In this presentation, we discuss ways of representing sinusoidal varying functions, specifically related to voltage and current in AC, and a way to represent those sinusoidal varying functions as something called a phasor, which is very similar to vectors, which you learn about in introductory physics. So a phasor is basically a rotating line whose projection on the vertical axis represents a sinusoidal varying function. So here's an animation of a line that's rotating in a coordinate system. It's rotating with a constant angular velocity, so it covers the same angle every second that goes by. And if you look at the projection, which is the purple line, of that particular rotating line, that projection is drawn in this picture that's moving, and that represents a sine function. And so this is a nice way that we can look at sinusoidal varying functions and represent it more in sort of a vector notation versus a sinusoidal function. Over here I have a similar picture. It's not animated, but here is my rotating line about the axis. Here's the angle that it's rotating through, and its projection here. I have a right triangle, and that's my angle, and my hypotenuse would be the maximum value of the line. And so the projection over here would be that maximum, which is the hypotenuse times sine of the angle. So that's where I'm getting that sine representation, because I'm taking that projection as it rotates and it's changing with respect to sine. And if this angle here changes in such a way that it's rotating at a constant angular speed, then the angle that it makes at any given time is just the angular speed times the time. And if I plug that into my sine function down here, I basically get a sinusoidal varying function. So, and that's just that projection of that phasor along the vertical axis. So just to sort of go a little further, and then we could look at this piece by piece. I'm going to go through this kind of quickly, but here's our phasor at different instants in time. And since these are equal time intervals, 1 second, 2 seconds, 3 seconds, and it takes 3 seconds to get to 90 degrees, each of these angles would be an angle of 30 degrees. So I could look at the projection. So at time t equal to 0, the angle is 0, I would be at 0. At 1 second, this angle would be 30 degrees, so the projection would be 100 sine of 30, which gives me that 50. And then the next angle here would be 60. 30 plus 30 is 60. And if I take sine of 60 times 100, I get 87. And then I get up to 90 degrees, and I'm all the way at the maximum, which is 100, and sine of 90 is 100. And so we could go through that for all of the different time intervals, and I see that if I go, keep going, another 30 degrees would be 120, and then 150 and 180, and then I get back to a 0 point. And we can see how that curve is starting to develop and look like a sine wave. And then if I continue on another second later, I'd be below the axis. And then I could continue and plug in those values, and essentially you can see that I get this sinusoidal function. And if I go around one complete cycle with this phasor, I'm back to where I started, and then the sine wave would start to repeat itself again. So it turns out that any sinusoidal varying function can be represented by this phasor, and the way that we represent it is not by the line actually rotating, because we can't represent a line rotating if we're doing things on paper, but we can represent it at time t equal to 0. And so we look at how that sinusoidal function is maybe shifted from one way to another at time t equal to 0, and that tells us where to draw our phasor in our phasor diagram. So in this particular case, I have a voltage which has some maximum value, and it's shifted to the left by some angle theta. So the angle here then, in my phasor notation, would be the angle that it's shifted to the left. And if I look at this and I look at the projection, so at time t equal to 0, because this is the time axis, At time t equal to 0, the voltage is actually not 0. It's some other value, and it's up here. And if I look at my phasor notation, the projection along the vertical is also giving me that same value. In other words, if I plugged in time t equal to 0 here, this term would just be 0, and I would have the maximum value times sine of the angle, and that's that projection right there. So let's consider some examples. So here I want to represent this voltage, which is 20 volts times sine omega t minus 60 degrees. And I do have to explain or at least represent what is the angular speed. It's not going to come into play when I actually draw my picture, but you do have to say, what is that angular rotation that it has? How quickly is it oscillating in time, or how slowly is it oscillating in time? And so I want to represent this as a phasor and a waveform. So first, if I represent this as a waveform, I realize that it's a sine wave and it's shifted by negative 60 degrees, which means that my sine wave, which would be here, is actually shifted from the 0 axis by 60 degrees to the right. So here's where sine would start if I was just drawing a sine wave, and it's shifted by 60 degrees to the right. And so if I were to represent that as a phasor, my phasor actually has to point below the axis, an angle of 60 degrees. And if I were to draw in at time t equal to 0 where it's located, here's that projection, and that projection, of course, is below the axis. So all I have to do to represent my phasor is to look at, what is that maximum value where the sine is varying, and then what is my angle, and then I just draw it in there. So this angle is below the axis, and that negative represents below the axis. What if I have something that looks like the voltage is 40 volts times cosine? This is more difficult because it's not a sine function. So let's just represent what cosine would look like. So if I were to just represent a cosine function, I know that cosine at time t equal to 0 is a maximum, and then I would continue to draw something that looks, like it's varying sinusoidally. So when I look at this, if I follow it back, I realize that cosine and sine are related to one another, and cosine omega t is actually the same thing as sine omega t plus 90 degrees. In other words, if I look at this, it's as if this sinusoidal function is a sine function that has been shifted to the left by 90 degrees, right? So this is time t equal to 0. To figure out where the sine should have started, it would have been over here by 90 degrees. So I could represent that as a phasor where my phase angle, because I'm looking at the sine function, is 90 degrees, and I could look at the projection. I don't think I made it on here, but there's the projection is exactly the same as the projection over here. So that last example should have indicated that, we're going to have to be able to convert between sine and cosine, maybe negative sine or negative cosine. And so there's some useful trig identities that we can use. So cosine omega t plus an angle theta is the same thing as sine omega t plus that angle plus an additional 90. If I had sine omega t plus an angle, it's the same thing as cosine omega t plus angle and subtract 90. And then if you have a negative sign, then it's the same thing as a positive sign plus or minus 180. So there's a lot of trig identities that we could use, but there's also a really simple way of remembering this and how to convert between sine and cosine and negative cosine. And if you learn this method, then you won't have to remember all the trig functions, or it will tell you what the trig relationships are. So when you're using this phasor notation to write the trig functions, suppose that I had the picture that's represented here. And suppose that in my picture, the angle with respect to the horizontal axis to the right is 110 degrees. And what I've done in this picture is I have labeled my axes in terms of sines and cosines. So my first axis that would normally be the x-axis if I was thinking about a traditional coordinate system is the sine axis. and then the y-axis is the cosine axis, and then the negative x direction is negative sine and then negative cosine. The reason that I've done that is because now if we think about measuring an angle in the counterclockwise direction, that's considered a positive phase angle, or a positive angle. I want to say phase angle, a positive angle. And if we measure clockwise, it's considered a negative angle. And that kind of goes back to what we just did a little bit ago when we measured one of the angles below the axis. But the other thing that's important is that I can measure the angle with respect to any of these axes. And if I measured, so here I'm measuring with respect to the sine axis, and I'm measuring in a counterclockwise direction, and that angle is 110, so this would be sine omega t plus 110. Now, if I used the cosine axis, here's my cosine axis, and I measure with respect to the cosine axis to where my phasor is in a counterclockwise direction, then that angle is 20 degrees, right? Because this is 90, 110 minus 90 is 20. And so I could represent that also as cosine omega t plus 20. So I don't have to remember the trig identities if I just remember this handy little way of doing things. So let's do one more. So suppose, or two more, I guess. Suppose I wanted to measure with respect to the negative sine axis. So I want to know where is this phasor with respect to negative sine. If this angle is 20 and they have to add up to 90, then this angle here is 70. So I'm measuring with respect to the negative sine axis, and I'm moving in a clockwise direction as I measure the angle. So I'm going clockwise, and that angle is 70. Clockwise is negative. So another way to represent this phasor would be minus from the negative sine axis, and I'm measuring with respect to that a negative 70 degrees. I could measure with respect to the negative cosine axis. So if I measured from here and to there, I have a 90 plus a 70, that should be 160 degrees, and it's in the clockwise direction. So, and with respect to the negative cosine axis, so negative cosine omega t, and then the angle is a negative 160. And you really could do this. I mean, I could also measure from this axis, from the negative cosine axis going this way, and that would just be a positive angle. So 110 plus 9, so this would have been 200 positive, and I did not write that one down.